Good morning, good afternoon, everyone. Thanks for joining us today. So I'm very glad to introduce Cristian Martinez from the Universidad de Rosario in Colombia. And he's going to talk about our recent paper on higher rank DT-PT wall crossing in Bridgeland stability. Cristian, please go ahead.
Thank you, Marcos, for the invitation. And well, the idea of this talk is to perhaps give you a tease of this paper that is coming. We have been working this, I think, about 2 years now. So I think it's a lot of stuff. So I don't pretend to do everything that we do in the paper, but perhaps just give you an idea of the type of things that we have been studying. So the title is this higher rank DT-PT wall crossing in regional stability. So let me start just by perhaps just talking about this rank one, the rank one case, right? The whole thing. Let me just move this a little bit. Yeah. So I will start with X. Take a smooth projective complex threefold, and I will take a curve class. And I will fix this Chern character, this 1, 0 minus beta, a Chern character vector. And this is just to say that n is going to play the role of the early characteristic. So stated to this Chern character vector, we have two modular spaces. The first one is a modular space of ideal sheaves with this Chern character, which is you can regard it as the Hilbert scheme, right? Just the ideal sheaves. And the second one is this modular space introduced by Pandaripande Thomas, that is modular space of stable pairs. So what is a stable pair? Stable pairs is a pair consisting of a pure one-dimensional sheaf and a section such that the section has no a section with zero-dimensional cokernel. The cokernel of this section is zero-dimensional. Then I can think of the objects that parameterize this modular space PV as complexes, actually, thinking of the section as this map from O to F, and regard this as a complex where O is in degree -1 and F is in degree 0, and then I can compute the Chern character for this complex, and I get exactly minus V. That's kind of the idea. That's where the V comes in. When X is Calabi-Yau, so this modular space actually have visual dimension 0, and things that people do with this counting invariance is that integrating these virtual cycles, one gets what are called the DT and PT invariants respectively. So DT, the Donaldson-Thomas invariants, are the virtual counts for the Hilbert schemes, and the PT counts or the PT invariants are the virtual counts for these PV modular spaces. Then there is actually a very interesting relationship between these two modular spaces, and this is the work of Stopp and Thomas. And they prove that actually there is a GIT wall crossing that relates these two modular spaces, the IV and the PV. So there is they can do a GIT construction, do variation to GIT, and prove that there is a single wall in this single GIT wall that separates these two modular spaces. And point-wise, they actually describe what are these modular spaces of the wall. They consist of, this joint union of these modular spaces they call I pure V plus K, that are just the sub-scheme of the Hilbert scheme consisting of ideal sheaves of sub-schemes of pure dimension 1. So they all basically curves of pure dimension 1, and it has Chern character V plus. So move a little bit this K, and they add it here with these symmetric powers. So they have this description for this variation of the JT, how these two modular spaces are related. That's one of the things. There is also a categorical. Somehow, let me this categorical DT and PT counts. And this was done by Bridgeland. And I like this way of thinking about this. Say, well, let's take T to be the subcategory of coherent sheaves consisting of all zero-dimensional subsheaves unless they derive orthogonal to them. That means all coherent sheaves such that there are no maps from zero-dimensional sheaves to F, right? Then this pair TF is actually a torsion pair, and we can consider this tilted heart, right? Where I take everything in F and I shift it by one, and then take everything in T, all the zero-dimensional sheaves, and I take the extension closure of that. This is the heart of the one of the structure. And then what Bridgeland observes is that an object, in the Hilbert scheme corresponds to a quotient of O, right? Really, it is the kernel, right? But if I try to measure all the kernels, right, then really I am also trying to count in all the quotients of O in coherent sheaves, right? In the category of coherent sheaves. And in the same fashion, actually the PT stable pairs actually corresponds to taking to counting quotients of O shifted by one in this category coherent, this category co-X, right? So somehow this counts, right? There is an intrinsic relationship between these two that is expressed in this GIT wall crossing, and also in this wall crossing somehow categorical, right? So the IV corresponds to somehow I can see relate this Hilbert scheme to quotients of O in coherent shapes, and the PT imbalance is quotient of O shifted by one in this tilted heart. And this is actually the observation, right, that allows Bridgeland to get this whole algebra identity that ends up finally actually proving this this DTPT correspondence, right? That is a relationship between the counts of PT invariance and DT invariance, and it's really this relationship that these two are actually. He looks at the class of these uh, quad stacks somehow in this whole algebra, and this relation, the fact that it's related by a tilde, these categories allows him to somehow get some relationships that end up giving him a nice proof of the DTPT correspondence. So that's on one side. So we have this GIT relationship. We have this categorical relationship, and then it comes actually with let's start with a little bit of Bayer's polynomial stability conditions, because in this realm of polynomial stability conditions, we can have a little bit more general notion of what is a DT stable object or a PT stable object, right? So let's just recall this. A polynomial stability condition is a pair ZA consisting of a heart of a modality structure A and a polynomial central charge. That is a homomorphism defined from the K group of the right category of X to the ring of polynomials, such that there is a real constant A, so that for M very large, the value of this Z function lies in this half plane, right? Consisting of all this all half plane. We say that it has phase between A and A plus one. And this is the condition. And besides that, this Z has the Hn property on A. That means that every, we can define perhaps what is polynomial semi-stable. So we can actually define each time that we compute the CE. Sorry. Each time that we compute the CE, right, we can write it as RE to the IP phi. This phi is called the phase. And we can compare the faces of objects, of sub-objects, and that is the way that we define for an object to be polynomial semi-stable. And then it has the Hn property, means that every object in this category A, in the heart, actually has a unifiltration, right, by polynomial semi-stable, with polynomial semi-stable factors, right? This kind of the definition. And while there is a suitable heart for these polynomial stability conditions that can be done very generally, this is also the work of Bayer. So he starts by considering this category less or equal than 1 of x, which is the subcategory consisting of all one-dimensional sheaves, or not just one-dimensional sheaves, but sheaves with dimension less or equal than 1. That's what it means. This little typo here. And then he takes the right orthogonal of that. That means all coherent sheaves supporting a dimension greater or equal than 2, and with no subsheaves of dimension less or equal than 1. And then he says, well, this also gives me a torsion pair. And I can again do this tilting construction, which is I take everything that is uh, as sheaf supporting dimension greater or equal than 2 with no subsheaf dimension less or equal than 1. I shift those objects by 1. I take all the objects with dimension less or equal than 1, and I take the extension closure of that. And that gives me a Harvard dispersion, which he calls AP. Then on this AP, he can define some polynomial central charges, right? And the way that he does is the following. So he takes an ample class on X and takes some complex numbers, 4 complex numbers, um, in such a way that if I take root 0, root 1, minus root 2, minus root 3, they all lie in the upper half plane, right? And he studies 2 different configurations for this. He defines this polynomial central charge, which is just taking row 0 times the 0 Chern character, row 1 times the second Chern character intersect with the ample class and multiply by n, and so on with row 2 and row 3. So he defines this polynomial central charge, and he studies 2 special configurations of these complex numbers, right? So he has one that he calls the PT configuration, and this one the complex numbers are organized this way. I have row 1, the face of row 1 is less than the face of minus row 3, is less than the face of row 0, and is less than the face of minus row 2. And he proves in this case that actually this ZA is a polynomial stability condition with A equals 0. So that means that the in the definition, I needed the polynomial central charge when applied in an object in the heart, right? Took values in some half plane. So A equals 0 means it takes values in the upper half plane for M sufficiency large. And he also proves that the rank 1 semi-stable objects of trivial determinant are precisely these PT stable pairs, so modulo shift by -1 in this case. So for this configuration of the complex numbers, he gets something that generalizes, right, this PT stable pairs. And then he looks at this other configuration, that is when row 1 is when he exchanged the order of these 2. So before we had the minus row 3 and the row 0 here, and now he puts these 2 complex numbers in the opposite order. And he then goes ahead and proves that this is again a polynomial stability condition with A equals 0, and that the rank -1 in this case, so there is a slightly thing here with the sign, but the rank -1 semistable logics of trivial determinant are precisely the sheaves by 1 of ideal sheaves of one-dimensional subschemes of X. So this is the way they call the DT, right? Also the counting ideal sheaves of one-dimensional subschemes. And then we can do this thing, right? That what happens if we have the DT, the PT, right? And we can think that this row 0 can approach this minus row 3, right? And if they start to move towards each other, right? Then at some point before moving from PT to DT, they have somehow to coincide, right? They have to coincide at some point, and this is actually a wall. So if we allow row 0 to be equal to minus row 3, then the polynomial stability condition ZA corresponding to this central charge polynomial central charge that we define lies on a wall in the space of polynomial stability conditions. And this wall separates what we call these DT and PT chambers somehow. But now, of course, DT, I'm talking about the polynomial DT stable objects with respect to the central charge, and PT stable objects are PT stable objects with respect to this polynomial central charge. Just that in the round 1, somehow they coincide with the ones that were known before, right? Now, other examples of these polynomial stability conditions come when we do can be constructed if we take a one-parameter family of Bridgeland stability conditions, which is a little bit more. Let's say that polynomial stability condition is somehow an asymptotic Bridgeland stability condition where the values of the central charge you only care about that they organize asymptotically. But for a Bridgeland stability condition, you want that the actual value or the function for every value of the parameter actually satisfies this inequality of the phases. Then we can take a one parameter family of Bridgeland stability conditions, define perhaps over the same heart, and consider what happens asymptotically when we let this parameter vary, right? This is the case of in this one of his first papers, Bridgeland, his Bridgeland stability conditions. Bridgeland proves that this large volume limit, when he fixes a heart, makes one parameter go to infinity and see what happens asymptotically, right? And he sees that this is related to the Gieseker moduli space, right? Then the natural questions, since we now have all these ingredients, we have the GIT wall crossing for these rank 1 DT PT moduli spaces. We have this categorical somehow wall crossing that allows us to think of these rank 1 DT and PT stable objects as counting as somehow measuring quotients of O or O shifted by 1 in two different hearts. Then the natural questions are, can we find perhaps a one parameter families of Bridgeland stability conditions on a threefold X such that their asymptotic stability corresponds to DT and PT stability? And if I can do this, can we realize these Badger's Stopa-Thomas and Bridgeland's wall crossing as a wall crossing, not just in polynomial stability as GIT, as something categorical, but actually as a natural wall crossing in the stability manifold. So these are the questions that we pretend to respond today, right? So for that, I have to tell you a little bit about how are stability condition threefolds. Of course, we won't be able to do this for an arbitrary threefold because we don't know a construction of a stability conditions that works on any threefold. So the closest, the nicest thing that we have is if we take a smooth project threefold of Picard round 1, and we have this construction for stability conditions due to Bayer, Macrì, and Toda that give us a three-parameter family of stability conditions in this case, right? And it's known that it works and actually produces stability conditions, geometric stability conditions, when X is either Fano, abelian, or quintic threefold, a general weighted hypersurface in one of these two weighted projective spaces, or a Calabi-Yau threefold obtains a combined intersection of a quadric and a quartic hypersurface in P5. So in these cases, just to show you that there are some examples that are worth looking at where this construction actually works. And then I will actually review it for you a little bit, this double-tilt construction. So for this, I will first take H to be an ample class that generates the Picard group, right? And then for every beta, for every real number beta, we can define this twisted Chern character, right? As twisting the useful Chern character for formally by this exponential e to the minus beta h. That gives me, I can write it this separated by degree, I get this vector, and then I can absolutely abuse the notation and refer to each entry in this vector as the actual twisted Chern character. Okay. So, and then we can do this first tilt. It's a double tilt, so we have to do this twice. But for the first tilt, what we will do is we'll take the Mumford slope. So CH1 over CH0, and here I will take it twisted. So it's a twisted Mumford slope. And I will define it as this quotient, the usual one when the CH0 is non-zero, and I will define it as plus infinity when CH0 is 0. Then I can take this to, because this Mumford slope has the Hannah-Simon property on coherent sheaves, I can take this torsion pair, first taking all the guys. Basically, this tau beta is generated by all Mumford semi-stable objects that have slope strictly positive, Mumford slope strictly positive, or I can define this as all coherent sheaves such that for every quotient of this coherent sheaf, the Mumford slope of it is strictly positive. And we can take this f beta, which corresponds to all those sheaves, such that no matter which subsheaf I take, this mu of f is less or equal than 0. So this gives me a torsion pair in very similar fashion of the ones that we talked about before, and then we can make this tilted hard. That in this case we call it co-beta because it depends on the parameter beta, and is the extension closure of taking this subcategory f beta and shift it all by 1, and then do the extension closure with this tau beta. Right? So we have this. This is the first tilt. Now on this first tilt, I can define a new slope, which is called the tilt slope, which is defined this way. Now I increase one parameter, so I take an alpha larger than 0, and consider this formula, right? This really is how you compute this tilt slope, which consists of taking the second twisted Chern character and subtract alpha 0 squared over 2 times CH0 and divide by CH1 beta. In the case the CH1 beta is non-zero, and in the case the CH1 beta is 0, then I just define as plus infinity. Then it's known, as has been proven, of course, a long time ago already, that this nu again has the Herrera-Simon property on this tilted category co-beta, and then we can take this, obtain a torsion pair exactly the same way. So the only difference now is that instead of measuring with the Mumford slope, I will measure with this nu slope. I say exactly the same thing, and again we get a torsion pair, and we can form a tilted heart, which consists of shifting this f, the elements in this f by 1, taking all the elements in t beta alpha, and do the extension closure of these two. And this is a second, this was called a double tilt construction because I have to do a tilt twice. And this heart is suitable to host stability conditions. And then in all the cases that I mentioned above, then there is a central charge associated to this. And this central charge adds one parameter to it. So for any s larger than 0, I get this now 3-parameter family of central charges. Or if I want to think about this, I can just fix the heart A beta alpha. And for A beta alpha, I have a 1-parameter family of central charges. And this central charge satisfies all the conditions that define a Bridgeland stability condition. And the associated Bridgeland slope, as usual, we take just minus the real part and divide by the imaginary part, is this number that is here. And we will call this Bridgeland slope as denoted by lambda. And then it comes here this very nice theorem that I like to call dt is horizontal. And this was proven by Marcos and Antony in the paper where they study the configuration of walls for Bridgeland stability on threefolds. And they proved that if I fix an alpha, a value of alpha, and a value of s larger than 0, then if V is the Chern character that has positive rank, then the only objects that remain lambda semistable when the beta go to minus infinity are precisely the Gieseker semistable sheaves of Chern character B. Right? This is a way I like to call it that we found the DT moduli space. Right? We didn't find it. This is the DT is the version of the Gieseker in higher rank, right? I mean the rank 1 DT corresponds to ideal sheaves, so we call the DT modular space as the Gieseker modular space when the rank is higher than 1. And then somehow we found these objects that are measured by these DT things, but in the limit. So we have a 3-parameter family of stability conditions. I fix 2 parameters. I let 1 parameter go to minus infinity. And then in the limit, I get this Gieseker moduli space. Now you wonder, well, what happens if instead of letting the parameter beta go to minus infinity, right? I fix the beta, I fix the s, and I let the parameter alpha go to infinity. Well, this is what we call vertical stability, and unfortunately, this description is not as nice. But however, there are two terms very long to state in this paper that we worked together with Marcos and Antony. And but then under certain hypotheses, it takes a friendly form. So let me just show you how are these objects, the objects that stay stable when alpha goes to infinity, and I have fixed the parameters s and beta, right? So the term is the following. So the hypotheses are here. This is to make it very nice to state. So it's take an S that is larger or equal than 1/3. This is because the walls somehow behave a little better. And take V Chern characters to find the Bogomolov inequality. That means, CH1 square minus 2 CH0 CH2 is greater or equal than 0. And I will take also the rank to be positive. And this assumption is very, very strong, that is taking the rank and degree to be co-prime. Then, in this case, an object of Chern character V is vertical semi-stable. That means that remains stable for a fixed beta, and a fixed S remains stable for all alpha sufficiently large. And here comes the caveat. This line description works when I take beta bar to be sufficiently negative. So when the beta that I fix is sufficiently negative. So when I do this, then an object of Chern character B is vertical semi-stable if and only if the following conditions are hold. First, that E is a complex that only has two cohomologies, 0 and -1. That the -1 cohomology is actually mu stable, Mumford stable. That the 0 cohomology has dimension less or equal than 1. And that the -1 cohomology is either reflexive, or when I take this double dual quotient by it, I get a pure one-dimensional sheaf, right? In general, I will get something that has dimension less or equal than 1, but for the objects that are vertical semi-stable, actually I get things that are pure one-dimensional. And this other condition is that no subsheaf of the 0 cohomology factors through the natural map that goes from E to its 0 cohomology, right? And this condition actually is going to be very important later. We'll give it a special name. But this is the description. This is what happens when I put this nice hypothesis. Then I actually can describe somehow how the objects that are stable in the limit are. And this, you see, this may look a little weird, all these conditions together. However, it motivates us to introduce this notion of stable triples. And then I like this because under this coptime condition, law has showed that a PTS stable object, in the sense of Bayer, Jason has showed that it satisfies all the conditions of this term. That means that every PTS stable object under these conditions for beta very negative is also vertical stable. And then this motivates to introduce this definition. Then a semi-stable triple is a triple BP eta, consists of B. It's going to be a 2 Gieseker semi-stable sheaf, such that when I take the double dual of B and I quotient by B, I get a pure one-dimensional sheaf whenever it's non-trivial, of course. It could be that it's reflexive. P is a zero-dimensional sheaf, and eta is a morphism in the direct category from P to B shifted by 2. This is like taking an X2 class somehow. And this morphism satisfies a condition that we call it completely non-trivial. And that means that no subsheaf of P factors through A eta to P, where A eta is actually the cone of, I take this morphism from P to be shifted by 2, and I can take the cone of this map, and I can shift it by -1. And this is called A eta, and then I get a natural map from A eta to P, right? This is just like saying that A eta, if I think of this eta as an extension from P, an extension of P by B shifted by 1, then this A eta is this extension. Then it has a natural map from A eta to P, and I don't want that any subsheaf of P factors through this. so that I can leave this morphism to E eta. So that's what we call complete trinomial. And then the interesting thing is that we can do some examples of these stable triples. And then, for instance, let's take an Fs to be a PT stable pair in the sense that we defined before. So F is a pure one-dimensional sheaf, right? And S is a section of F, so it has zero-dimensional cokernel. Then I can take the image of this S, and this image of S turns out has to be the structure sheaf of some pure one-dimensional subscheme. And this is because the F itself is pure, so it has to be a pure, it's a quotient of O and has to be a subsheaf of F, so it has to be pure. And then if I take IC to be the kernel of this S, of this section, right? This is a 2 Gieseker stable, and we have this exact sequence. So we have the natural thing, right? This morphism from O to F has quotient that is P, and the kernel is IZ. Then and this P is zero-dimensional because it's the definition of F. And then this, I can look at these two guys in the middle, this O to F, and I can think this as a complex, and I call this complex A eta. And this A eta turns out to be an extension of P by IC shifted by 1, right? Because this is what it's doing, right? This is just an extension. I can think of this central part of this complex that's an extension, and this ends up being a morphism from P to I2, right? So, and if a sheaf of P factors through A eta, right? If a subsheaf of P factors to this thing, but it has to factor to the degree 0 part. So it will have to factor through F, but that will contradict the purity of F, right? Because a sub-zero-dimensional sheaf, and then F has no maps from zero-dimensional sheaves to F, right? So it's completely non-trivial. And then this just shows, right, that this our definition of stable triple includes in particular these PT stable pairs, the round one that were defined before. Then if I take this ideal sheaf of C, this P and this eta corresponding to, right, the eta corresponding to this complex, right, seen as a morphism from P to I2, then this is a stable triple. And also it works on the opposite direction. If I take a round one and determinant 0, a stable triple, thinking of that the Chern character of this is just the Chern character of the object A eta that we define. So if I take a stable triple, and then because P is zero-dimensional, it doesn't affect the Chern character, only the CH3, then saying that has rank 1 means that CH0 of B has rank 1, and the CH1 of B is 0, means 0 determinant. Then since B is a torsion-free sheaf for rank 1, right, because 2 Gieseker semi-stable, then B has to be some ideal sheaf of a curve, and so with a line bundle for some, not necessarily a pure curve, but a one-dimensional subscheme, and a line bundle of degree 0. And then when I compute this home from P to this B shifted by 2, right, I get this group that turns out to be the same as home, right? Because I can just move this L to the other side, and then P is zero-dimensional. Then this is the same as home from P to IC shifted by 2. Then that means that when I take this extension class, I may as well just assume that the sheaf B is just IC, right? And now I can try to compute what is home from P to IC shifted by 2, and just using the long exact sequence, the short exact sequence that goes from IC to O to OC, I get that this can be written as an X1 from P to OC. And then that means that this extension class can be thought as an actual extension in coherent sheaves of a zero-dimensional sheaf P to the structure sheaf OC. And then this F must be pure since C is, right? Because this is the extension, right? Anything that and then and because the extension is completely non-trivial, right? So if there is somehow something zero-dimensional, right? As a zero-dimensional associative of f, right? I can think of this as something that factor through p, right? And then we'll have to actually this composition had to be zero, so we'll have to leave to OC, but it's pure, so it cannot be. So what I get is an honest PT stable pair. So like PT rank one determines zero, PT stable pair and stable triples are the same, right? And then actually we have this term that is one of the things that we prove in our paper, and I like to call it here PT is vertical, and says, well, under this nice assumption that S is larger than 1/3, P is a Chern character with V0 negative. Here I want to put V0 negative because I want to think that V0 is the CH0 of the object A eta, and that it will be minus the CH0 of B, right? And then I will take V0 to be negative, and V0 and V1 co-prime. Then there exists a constant V0 negative, such that PT stable objects, vertical stable objects, and stable triples of Chern character V, they all coincide. What that means? It means that PT stable objects are exactly the vertical stable objects of Chern character V for every beta less than beta 0, this beta 0 that exists, and are exactly all the complexes A eta corresponding to the stable triples BP eta. This is the theorem, of course, as will be absurd to try to prove this here because it's a very long computation. But somehow, schematically, what I want to show you is this. So we can fix an S. When we fix the S, we get these two parameter family stability conditions, right? The beta and the alpha. And somehow we have these two things, right? That is a value beta 0 that depends on the Chern character. Says that if I move vertically here, right, I get these vertical stable objects that are exactly the same as the stable triples and are exactly the same as the PT stable objects. So in this direction, vertically, I get PT. And I had this other part, right? That is the part that Marcos and Antony showed, is that if I fix a value of alpha and I let the beta go to minus infinity, then here in this limit, I get dt. So I get pt and dt as two limits, one horizontal, one vertical. And the natural question is there a wall? Is there a wall that separates them, right? So somehow in the limit here, if I move here diagonally in the limit, I should be able to see the wall of Bayer, right? In polynomial stability, because I should think of these two as two polynomial stability conditions. So in the limit, I should get this wall. But the question is, can I see this wall, right? In the space of Bridgeland stability conditions? And the answer is yes. So the wall is this one. So let me define for you. So I will fix the Chern character V and S number larger than 1/3. Again, this is for for the consideration that we have, the terms that we're using. And we will define theta B to be this is a curve in the beta alpha plane consisting of all those beta alphas such that when I compute the imaginary part of the central charge in V, I get exactly 0. I can go ahead and see what is the imaginary part of the central charge, and it's exactly 2ch2 beta V. It's a ch2 beta V minus alpha squared over 2ch0. So that means the equation that defines this curve is exactly this, 2ch2 beta V equals to alpha squared ch0 V. And then we have this proposition, and this is what motivates us to see how to look at this curve. It's a proposition in the paper by Marcos and Antony. It says, well, if you take a beta bar, alpha bar over this curve, then an object of Chern character V is Bridgeland semi-stable if and only if it's a complex that has only two cohomologies in degrees -1 and 0, where the zero cohomology is a zero-dimensional sheaf, and the -1 cohomology is actually tilde semi-stable. So tilde semi-stability comes into place, right? So they say the only objects that are stable on a point on this wall are two-term complexes, but where the zero cohomology is zero dimensional, but the minus one cohomology is still semi-stable. So I come here that the issue, right, that we have to then, before understanding these objects, I will have to understand the till semi-stable objects. Fortunately, this is and then this is very similar to what we had with these PT stable things, right? Just that for the PT stable, we have H minus 1 of E to be 2 Gieseker stable, right? So semi-stable. So I would like to relate this new stability with 2 Gieseker stability for me to be able just to say, okay, this is something I can do. Fortunately, so there are some known facts. And here I go. So the walls for till stability are, when you compute them and draw them, they're all nested semicircles in the beta alpha plane. If V is a Chern character that has positive rank and satisfies the Bogomolov inequality, then the till walls, the walls that appear, actually are bounded. And moreover, this bound depends only because the new slope, right, only depends on CH2, CH1, and CH0 doesn't contain CH3, then this bound depends only on V0, V1, and V2. So you can vary the V3 as you want, and you're not going to get any more till walls. Another thing is that if you fix the value of beta, such that beta is less than V1 over V0, which will be like the Mumford slope here, okay? Then the only objects that are non semi-stable for large values of alpha are the two Gieseker semi-stable sheaves, right? With the first Chern characters in V0, V1, and V2. This is very similar to the proof of Bridgeland for surfaces when he computes this large volume limit computation. So it is telling that if I take beta sufficiently negative, then I know that the two Gieseker semi-stable sheaves appear, right? Appear as still semi-stable objects when alpha is very big. So if I combine all this and the fact that there is a outermost wall, right, because the walls are bounded, then an object that is lambda semi-stable for some beta bar alpha bar on the this curve theta v, and if the beta alpha is a point that is above the largest wall for till stability, then this object, right, will have to be two Gieseker semi-stable. Then I have this characterization for which objects are Bridgeland semi-stable for points on the curve theta, as long as I am after the largest wall for till stability. And it says, so an object is stable at a point at this curve if the point is above the largest till wall, if and only if the minus one cohomology is a two Gieseker semi-stable sheaf and the zero cohomology is zero dimensional. So, what are the stable objects of the world then? Right? Because I hear I have the semi-stable, where actually the strictly semi-stable. Then that's what we want to study in detail. So let me take beta v, alpha v, the intersection of the largest till walls. So remember, the till walls are these semicircles, right? That are somehow nested, and the radius is bounded, so there is a largest one, and this largest one intersects this curve theta, right? And let's take this point of intersection to be this beta v alpha v. So I'll show you a picture in a moment of how this looks like. Then we prove the following theorem in our paper. So if you take a beta that is less than this beta v, right? So it turns out that the curve theta v actually, you know, goes to infinity, right? No, see, yeah, it grows as beta goes to minus value of beta that is less than this value beta v, right? Then you are actually going up in the alpha, right? And then let's take this beta alpha, a point on theta v. Then the Bridgeland semi-stable objects of Chern character v, a Bridgeland semi-stable object of Chern character v, is S equivalent to a direct sum of the form B shifted by 1 direct sum with P, where B is a 2 Gieseker semistable sheaf and P is a 0-dimensional sheaf. Moreover, the objects that are Bridgeland stable, I should have put here the beta alpha S, right? Also depends on the parameter S. Stable if and only if is of the form B shifted by 1, right? So with this condition here, all this I'm taking the same hypothesis, right? Like B0 is strictly positive, strictly negative for this thing to work. So the only thing that is stable, right? One thing of these guys that are stable are actually of the form B shifted by 1 for some 2 Gieseker semi-stable sheaf. But not just that, it cannot be just Gieseker stable. That's not the only condition. There is another condition that shows up, and is that B double dual quotient by B is a pure one-dimensional whenever it's non-trivial, right? Then I would like to show you a sketch of the proof for this because I think it has very nice content. So how it goes? So if you take B to be the -1 cohomology of an object that is stable at the wall, and P to be the 0 cohomology, then we obtain the first part because this was the description that had the Jardim and Maciocia for objects that are semi-stable at the wall, just combining them, right, with the fact that the new semi-stable objects at this point are exactly the 2 Gieseker semi-stable sheaves, right? So, uh, well, and then we get also, right, we have the sequence, the stack sequence corresponding to the cohomology. So I can split E by its -1 cohomology here, B, and then get the B shifted by 1, maps into E, and then has a quotient that is P, which is the 0-dimensional, the 0 cohomology of E, right? And this turns out to be a destabilizing sequence because at the wall theta, because theta is defined by the imaginary part of the lambda slope, then the lambda of B is actually plus infinity, which is the same as the lambda of a 0-dimensional of an object that is of a 0-dimensional sheaf. So they are both infinity, so this actually corresponds to a wall, right? And then at theta, right? Because these two have the same slope, right? So E has to be as equivalent to the direct sum between B shifted by 1 and P, right? This is what happens. This is you can continue splitting the Jordan-Holder filtration, but you can use B shifted by 1 and P to construct Jordan-Holder filtration for E. Now, if B is, then you go ahead because you say, okay, well, I want to check what happens and when these objects that are S equivalent to B shifted by 1 direct sum with P are actually stable at the wall. So if B is strictly to Gieseker semi-stable, and I take the stabilizing sequence in coherent sheaves, then one can prove that if I shift all this by 1, this continue being a stabilizing sequence for now lambda stability. And then there will be a contradiction if I am assuming that B is lambda stable. So that means that B has to be 2 Gieseker stable and not 2 Gieseker strictly semi-stable. Right? That's for that part. And now comes the interesting part, and it's proving that if it's stable also, this B double dual quotient by B is pure one dimensional. So let's call this quotient by QB. So QB is B double dual quotient by B. If it's not pure, then I can take its maximal 0-dimensional subsheaf. I call this by ZB, and I can take the quotient of QB by ZB, right? And then if I take B prime to be the kernel of this composition, so I go from B double dual to QB, and they take a further quotient of this TB. So we have this diagram in coherent sheaves, right? So I have B injects into the double dual, has quotient QB, right? Now QB has a 0-dimensional subsheaf, its maximal 0-dimensional subsheaf ZB. And then, so that TB, that is the quotient, is now pure one-dimensional, right? And then I get this little diagram. I can take here equality from B double dual to B double dual, and I can take the kernel from this composition from B double dual to TB, and that's B prime. Then B ends up injecting in B prime, and then by the snake lemma, I know that the cokernel of this morphism from B to B prime is exactly the same as the ZB, right? And then what does it say? That means that if I rotate this, right, I shift this B by 1 and B prime by 1, then I get this short exact sequence. And that turns out to be a destabilizing sequence of B shifted by 1 because this ZB is zero dimensional. And this are zero dimensional has infinity lambda slope. Right? So ZB ends up destabilizing B shifted by 1, and then B shifted by 1 could not be stable possibly. So that means that the B that I started with had to satisfy that the QB is actually pure one dimensional. So this condition comes to place here. Now I want to check in these last 5 minutes what happens nearby, right? And these are very general things that happens when you have a wall, right? So let's fix a Chern character, satisfy all these nice properties, right? So I will check, we'll take it with zero rank, negative rank, sorry, and so that this coprime condition between the rank and degree, and I will take a beta that is less than this beta v, this point of intersection of the largest steel wall with the theta curve, and I will take B a 2 Gieseker stable sheaf that has Chern character what I would like to have, which is the negative of the V, and so that has homological dimension 1. That means it has the B double dual quotient by B is pure one dimensional. So we have the following behaviors there. At the wall, I know B shifted by 1 is stable because B double dual quotient by B is pure one dimensional and B is 2 Gieseker stable. And the shift B, because it's a zero dimensional shift, right? This is only semi-stable. I cannot say that it's stable, but it's semi-stable. And then besides that, the wall, right? The lambdas of B shifted by 1 and the P are all both equal to plus infinity. And every extension of P by B shifted by 1 is S equivalent to B shifted by 1 that I sum with P. Right? Every extension that I take is going to be S equivalent to this at the wall. But if I go above, I'm very close to theta V, I will see that actually the lambda of B shifted by 1 is less than the lambda of P because the lambda of P continues being plus infinity, right? And if I go very near this wall, the B shifted by 1 that was stable at the wall is still stable above because being stable is an open condition. And then I can take these extensions, right, of B shifted by 1, of P by B shifted by 1, and then I can prove that every completely non-trivial extension, again, that means that no subtree of P factors through A, that continues being stable above and very near theta V. That means exactly the PT stable objects. That means just above the theta curve, I get the PT chamber, an object where all the PT stable objects, a region of the stability manifold when all the PT stable objects are stable, right? Under these nice conditions, of course, on the coprime conditions. And then the next question, and not just that, but I also have a contracting morphism, right? That goes from the PT modular space to the modular space of the wall. And that sends an object A, which is the PT stable object, to its S equivalence class at the wall. And the S equivalence class at the wall is the H minus 1, the degree minus 1 cohomology of A that I sum with the 0 degree cohomology of A. Right, that's what I get, is this contracting morphism from one side of the wall to the wall. And then I can also go very near theta V and below, and then there is a technicality here because we fix the rank to be negative, then there are no lambda semistable objects. You can prove, right, it's an empty condition to have lambda semistable objects nearby and below theta, which are character V because the rank is negative. So one can bypass this issue by, instead of considering the category A beta alpha, which is the slicing, the standard slicing of things that have phase between 0 and 1, we can consider slicing that has the objects that have phase between 1/2 and 3/2. It's just a technical thing, but allow us to modify a little bit. And what we do is instead of we take a different heart, a heart that's slightly different, right? And where the stability is measured by this lambda slope. And this lambda slope is basically taking, changing the order of the real and imaginary part. So that's why it changes in the order. I think there is a minus sign that I forgot. But there should be a minus sign. It should be minus this number. So we can measure with this Bayesian slope, and then when we go at theta v and we analyze again with this lambda hat slope, then a PT stable object that was of this form, right, an extension of a zero-dimensional sheaf by b shifted by 1, right, that becomes a destabilizing sequence because precisely, right, and now I change the denominator, move to the numerator part, and then instead of before I had lambda taking the value of infinity at b and b shifted by 1, now because the denominator is on the top, right, I will get the lambda hat of b shifted by 1, the lambda hat of b equal actually to 0. And that means that this A is actually destabilized at theta v, and that becomes an honest wall in the sense that we can cross it. So I can wonder what happens below this wall. Well, at the wall, b shifted by 1 is stable, and the standard error wall shows, again, same as we did for just a little above, works a little bit below. If I take the flip extensions now, if I change the order of these things, these objects are stable nearby and below theta v, right? Because I can show that below theta v, the lambda hat of p is less than the lambda hat of p shifted by 1. And then you can work a little bit more using, long exact sequencing cohomology to show that actually that E that fits in something like this is the sheaf of a sheaf. And not just of any sheaf, but a sheaf that is Gieseker semistable. Right? So this extension is actually the sheaf of a Gieseker semistable sheaf. And then I would like to say that we found the DT chamber, because then the DT counted the Gieseker semistable objects, and those objects all are semistable just below, right? And then you can go work a little bit further and say, what happens, right, if I rotate that triangle? Because now I know that E is F shifted by 1, and if I rotate that triangle, I get this short exact sequence in the category of coherent sheaves. And then that means that B, right, was exactly the sheaf F prime construction the proof that theorem above, right? That was it, because it's this B, right? This F was a Gieseker semi-stable sheaf, but B was two Gieseker stable sheaves such that B double dual quotient by B was pure one dimensional, right? So B is the kernel, really, of the morphism from F double dual to this TF, right, with this pure one-dimensional sheaf. And then it means that we get a contraction, because now I know, right, what the contraction should be, right? The contraction should take, right, an object. The object that I wanted, right, was exactly the E, which was F shifted by 1, right? And F shifted by 1 should go to contract at the wall at the S equivalence class. And the S equivalence class is the same S equivalence class of this sheaf F prime shifted by 1 that I examined with the TF. So somehow decomposes. So I would like to say, we would like to think of this contraction now as an analog of this Gieseker-to-Uhlenbeck map. This is kind of what happens. I can summarize here. The theorem says that, well, under all these nice conditions, I get this wall crossing now in the stability manifold, the Bridgeland stability manifold, right? That relates the Gieseker modular space and the modular space of PT stable objects, that here I call it TV, the modular of the stable objects, the PT stable objects, thinking that also parameterizes stable triples, right? And the morphisms are given by, the Gieseker to the wall. It just extracts this E prime sheaf shifted by 1 and add this ZE part, right? And the other was just taking the cohomologies. That was the S equivalence classes. At least said theoretically, that's what happens. Then the picture is kind of like this, right? I have this red here, red curve represents the largest steel wall. The theta V curve is like this blue curve, kind of. This is the maximum point of intersection. Then nearby theta V, I have the DT chamber and the PT chamber. And of course, there are other regional walls around there, around that can, uh, just change the shape of these PT chambers a lot. But we also prove in the paper that actually only find remaining of those. So if you move beta negative enough, then you can avoid those issues, and you get exactly this is the picture. So yeah, that's what we like to call the DT-PT wall crossing in Bridgeland stability now, not just as JT or categorical, but actually in Bridgeland stability. Well, that was all what I had to say. Thank you.
Thank you very much, Cristian. Are there any questions or comments?
I have no questions, but I'm very much impressed with this work.
Thank you very much,
So
Alexander.
Part of a big program that you are doing now with your group.
Yeah, it's been several years. So I went to Edinburgh in 2017 to start learning these things with Antony, and it's been several years. First the 2, and then the 3, and now the 4th of us working together.
Yes. Mm-hmm. So thank you much for this introduction.
Thanks,
to this
Alexander.
program. Mm-hmm.
Any questions?